Hello, everyone, and welcome to the second session of our Tech Talk series with Confluent. Before we begin, I have a few quick announcements. This session is being recorded, and a link to the recording will be sent to everyone who registered. If you have any questions, please submit them using the Q&A feature in Zoom or by typing them into the chat box. We'll answer all questions at the end of this session. With that, let's jump right on in.
All right, thank you. So my name is Mike Peacock. I'm from Confluent. I'm currently a director of solution engineering here in our public sector group. Prior to that, it's a newer role for me, but prior to that, I was a solution engineer that covered a lot of the public sector, but a big focus on the DoD. So in the DoD and basically across public sector, we do see a lot of use cases where the edge is involved. So that's today's talk is how we're empowering the edge with data in motion. So welcome. We'll glide through the slides. I'll show some example architectures, get a little bit into Confluent and why we're saying we can use Confluent at the edge, challenge some traditional use cases with Kafka. When you think Kafka, you probably think more of a larger data center deployment, but we're here to say you can use it for a lot more. And then dive into some government use cases and a little bit more. We'll leave plenty of time for Q&A. So hopefully we get through the slides quicker with plenty of time for you guys to ask any questions you may have. All right, let's get a little bit overview on the edge and how we see it today, especially in the public sector landscape. So there's obviously been a big push for cloud computing for a number of years, and there's no denying that there's a lot of efficiencies to be gained there. But what we often see now is that the edge is becoming increasingly more important. And we're seeing a number of use cases across not just the commercial side, but again, public sector. So things from manufacturing, manufacturer plants are getting smarter. They want to push a lot of automation down to the plants, do predictive maintenance. In the retail and commercial e-commerce side, my partner Andrew Jacobs did a talk last week on logistics, and a lot of that was how we do logistics at the edge. So again, we're seeing a big push there. When you start looking at transportation, there's a ton of automation obviously going into vehicles and sensors galore, right? If you buy a new car today, it's always connected, and there's a ton of sensors to be gathering information and even some automation and analytics being run at that edge. So a car is an edge device. When you look at healthcare, there's things like what we can do from a patient information, again, in the room itself and across the hospital, and then you propagate that up to more of a global view from a global healthcare perspective. So hospitals as an edge, and then what we can do from an AI automation perspective at the edge. And then the last area, and we're going to focus a lot on that, obviously, being a public sector talk, is in the government space. It could be things from disaster response operations, remote field, deploying soldiers again from something like a command post. So they're off on the edge collecting information, and then just general military operations. So we'll dive a lot deeper into that. Some quick terminology, just so we're all on the same page. I'll be talking a lot about these types of things. So I just want to make sure, again, it's consistent across the board. So when we talk about the edge, there's a couple different deployments. We talked about cloud, right? Obviously, with a cloud deployment, you don't have to consider as much that you do in the edge, meaning you pretty much have unlimited compute and storage. So what you deploy in the cloud is not as significant in these edge types of devices. So different types of edges. You talk about thick edges, right? In that sense, we're talking about something maybe on-prem or where you have more compute and storage. So you definitely need to factor in what you're deploying and what you're using from a compute and storage perspective, but it's not as strict and you can do a little bit more. In this case, we're talking more traditional deployments where if you look at Confluent or Kafka, you can deploy an entire cluster. When you get down to the thin or far edge, you definitely have more things to consider. You have very lightweight compute, very limited storage, and you really need to start looking at things like size, weight, and power and how that impacts the device itself. So these are the areas that we focus a lot on and what we can do at those thin edge devices. But the thick edge, the cloud, everything comes into play when we start looking at how we share that data across every enclave. And the last thing we see often, and we see it more, we hear about DDIL, which is denied, disrupted, intermittent, and limited connectivity. We hear about that more in the DoD as a term, DDIL, but honestly, in any edge use case, you can never guarantee that you have connectivity up to, say, a cloud environment. So you always need to plan for some disconnect from a network perspective, and you'll obviously need to continue operations, which is critical. So you definitely need to plan for these DDoS use cases, and we'll talk about how we're handling a lot of that in the government space today. So a couple of reasons why you would want to run, you know, any software at the edge. So one thing I talked about continuity of operations. Uh, if you have a disconnected edge use case, like I talked about DDoS in that case, you definitely need to have some level of operations running at the edge. So never plan for full connectivity. So in this case, you're shifting things more as much as you can, that is to the edge devices. In some cases, it's time. There's network lag, right? Depending on what that, you may have connectivity, but you may have bandwidth constrictions. So think about from a time perspective, how long it takes that data to get from the edge up to a cloud environment where you may be doing, say, analytics, but you don't have the right response times to get the inference needed at the edge. We see a lot of customers looking at everything from a security perspective. So again, in public space, very critical. So as we push things more to the edge, how can we secure those environments? And in some cases, if you're secure at the edge, then you're secure throughout. And the last thing we see is cost, right? So one thing we try to help customers do is restrict the amount of data that you're sending from the edge up to your higher enclaves. And one way to do that is with stream processing, where you filter out that data, you aggregate. There's usually a ton of redundant data at the edge, depending on the sensor collections. So we try to help in that case too, which reduces overall cost, increases performance, and we call that terminology shift left. You'll probably hear that often from, if you talk to anybody from Confluent, you hear shift left. That is basically moving everything closer to the source of data as much as you can. And when it comes to the edge, you really can't shift any further left. So it's a critical thing in what we describe for our customers. All right, so diving in, we'll go over some example use cases. I'm not going to dive too deep, so we'll keep things at a higher level. We'll dive into example use cases a bit later. So if we look at the 1,000-foot view of some sample architectures, again, very simple here. So all we're trying to say is that you have one-to-many edge devices, and typically it's a lot. Those edge devices are collecting information, whether it be sensors, whether it be on-prem, something like a ship, for instance. You may not think of a ship as an edge device, but it is, because it's just a large data center. It's at the edge. It runs independent, never plans for connectivity. So you may have more storage compute in there, less than a drone, obviously, but it is an edge device nonetheless. Each one of these edge devices collecting information where you're now linking that up to, say, a cloud environment where you can do deeper analytics. You can do long-term storage and whatnot. I have cluster linking on this slide. We'll get into a lot more of that. It is a critical piece. In the Confluent respect, we use cluster linking to connect, say, a cluster running at the edge to a cloud environment, and it handles all the synchronization for you. But I'll dive deeper into it coming up. Getting a little deeper, say a 500-foot view, sensors on the left is usually a sensor integration level layer, because not all sensors have the identical interfaces. Unfortunately, it's not a common interface for all sensors. You have things like RESTful interface, pretty common default type of interface. Doesn't handle a ton of throughput. You can do a good amount, but typically REST is there to get the data, and hopefully the throughput works in that case. Where it doesn't, you may have some native Kafka support. Kafka is pretty ubiquitous across any environment, and we are seeing an uptick in, say, IoT devices that speak direct native Kafka. Outside of that, we have a ton of connectors, a lot of open source connectors that can really do a lot of the heavy lifting for those connectivity issues. And then lastly, you'll see things like MQTT. especially in the IoT domain. And you can always do a custom interface, but that's that sensor integration layer where you're bringing all the information in up to, say, a Confluent instance running at the edge, where you can do some stream processing, again, depending on what your size, weight, and power allows you to do. Some AI, ML inference, can't get away from that. And then ultimately pushing it up to a cloud environment, again, where you're doing model training, deeper inference, some dashboarding, you get a more of a global view. And then finally diving specifically into different edge devices and cloud environments. So if you start with the thin edge at the bottom there, typically we'll run just a single broker, Kafka broker in those environments. They're being used as that aggregation point. If you have enough size, weight, and power at that thin edge, you can do some stream processing, a couple different ways to do that. But that is really where you can start filtering out or aggregating data in that layer. Move up to the stack, you already have thick edge, right? So usually you have a bit more compute and storage. Maybe you have the capability of running, say, a high availability cluster, multiple brokers. You can run a connect cluster, or you can using that to bring in some static data, whether it be databases or whatnot. Maybe a control center UI to manage the environment. And then the last one, maybe Flank, right? You get more powerful stream processing capabilities in these thick edge compute stacks. Using cluster linking for both of those to push up to a cloud environment where you now have aggregation across many different edge devices, doing way more powerful things from an analytics perspective, maybe model training. The one thing I want to call out here is from a deployment strategy, you always need to think about how you're going to manage these edge devices because, again, you can have hundreds, even thousands, and how you manage those becomes critical, right? One's out of date, or you need to push an update, or maybe an enhancement, maybe an ML model. So how would you do all that? From the thick edge or even thin edge, you do have the capability of running something like Kubernetes to manage it, so it becomes much simpler. You use the Confluent operator for all that. Thinner edge environments, we typically see something like K3's thinner version, lightweight of Kubernetes. And if you don't have the Kubernetes expertise or can't run it, you can always use Ansible to deploy these across the environments. Just some food for thought there. All right, let's get into a little bit about Confluent and why we're saying, look at Confluent as a possibility to deploy at the edge for sensor aggregation. First off, who we are and where we came from, just to give a level set, give us some credibility, right? So if you don't know who we are our co-founders of Confluent, or the creators of Apache Kafka back in LinkedIn. They created Kafka again to be able to handle large volumes of data, high variety, high velocity. That's what Kafka was built for. From a Confluent perspective, we focus everything you see on there, and I'll go a little deeper, right? We focus on ease of deployment, security, 100% for our government customers, and things like data governance are huge. If you look at what Kafka again was built for, data at its very simplistic form, and that really has unlimited number of use cases when you think about it from a data perspective. So here's some examples we see more on the commercial side. The financials are huge. 10 out of the top 10 banks are using Confluent to process this data in real time for things like fraud detection, for example, payment processing. You probably are using Kafka or Confluent more than you think, and things like Uber for real-time tracking, or even logistics information from a lot of the top stores like Walmart, for example. If you dive into more public sector use cases, well, these are some high-level examples, but starting from the left side, you'll see that we're being used for ship-to-shore comms. This is a primary focus of what we're talking about today. I'll dive into more of that, but again, looking at how we can get that edge data to a cloud environment, pretty simple and consistent. Used across ERP systems, logistics, big part of, again, what my partner Andrew talked about last week, healthcare, and then the last one is cyber and SIM. Surprisingly, Kafka is a big player in that because of, again, why it was designed with the high variety data, high velocity, but being able to broker that out to many different environments also. when you look at it from a very high level perspective, this is what we're trying to build from with Confluent, being that connective tissue between all these different data sources, these siloed approaches, being a conduit for how you can share and enrich real-time data. A bit of the focus, and this will come into play with stream processing and at the edge, right? So if we look at the stream layer, that is really what we're talking about. A big focus here for the edge side, where you can deploy and manage your data anywhere. We'll dive deeper into that one. Connect is how you connect to a lot of different systems, whether it be databases or message systems, what have you. Large number of connectors available to be able to do that quick and easy. The processing layer becomes critical when you want to filter and aggregate data. And the last part, like I said, governance. Can't do anything in public sector without having a good governance strategy. That's as simple as security, securing the data from rest at rest and in flight, and then putting some other governance things on top of that, from data contracts and just making things more compliant and trustworthy. So that's enough about Confluent. Again, just trying to level set who we are and why we want to be a player in this field. Let's talk about challenging some traditional Kafka use cases. I talked about the streaming capability and deploying everywhere. So typically you may not think of Kafka being deployed at the edge. And hopefully by the end of this talk, you can see that it is certainly possible and should be considered in your architecture. But you typically think about Kafka maybe running in the cloud in a large data center, on-prem, again, using a lot of size, weight, and power. With Confluent in a mix with some of the capabilities we have, we'll get into, definitely consider running at the edge too in these small footprint environments. A big piece of that is a capability we have called cluster linking. Like I said earlier, this was designed to be able to just link one cluster to another. Originally designed for something like a disaster recovery use case to keep maybe a hot and a standby cluster, or double HA, right? From a a DR perspective, or just sharing data across multiple environments. That was its original intent, but it happens to work really, really well in these DDoS use cases. So let me step back and give a bit of, say, a Kafka 101, not too deep, but it'll help understand why cluster linking is powerful and how it's sitting on top of basically what Kafka does. So when you talk about Kafka, you hear events. An event really is just anything that happened. It's a transaction that occurred in your environment. It can be anything from, say, a shipment being delivered, a vehicle position updated or changed, a sensor went offline or online. Anything that occurs from a transactional perspective is considered an event. That is the foundational piece of topics in Kafka. When you look at a topic and what it's made of, again, a bunch of events are stored in the topic in an immutable log. And this is key for stream processing, because when it's immutable, obviously you can't change that data. It becomes a program of record in that sense, where or a fact, right? You can't go back and change it, but now you have a whole transactional history of everything that occurred for that specific topic. When you dive into the consumers and how they read that data, they can pick and choose where they want to read that data from. So if they need all the transactions that occurred, they may start from the beginning and process each one independently, or they can pick to choose from the latest and start getting all the information from there on out, or they can look at a point in time and start consuming. What's critical with this and how it becomes really a decoupled approach is that each one of these consumers has an offset associated with it. That offset's maintained independently of each consumer. So you can have something like a slow consumer not impacting say, a real-time consumer. And this becomes super critical with something like cluster linking that resides on top of this. I'll get into it here, right? So in normal operations, cluster linking, say from an edge device to a cloud environment, events are synchronized, no problem. You have full connectivity. Every time a topic is synced with the cloud, that offset's updated and retained for that specific topic. Now, let's say we have a disconnected use case, a DDoS use case, whether again, intentional, non-intentional, can't plan for it, but you need to continue operations. So events, all the operations of the edge device will continue on. You're consuming data, every event's retained in Kafka. However, you don't have that cloud connectivity. But the last thing that was retained for that cluster link was that previous offset. So when connectivity is resumed, cluster linking will pick up automatically for you and start syncing exactly where it left off from the last communication. So you can see it's a really critical player when it comes to DDoS. Wasn't originally designed for that, but it just happens to work really, really well in these cases. All right, let's get back to the edge talk because again, that was a foundational piece that I really wanted everyone to walk away with from a Kafka perspective and cluster linking. So again, hoping to break this paradigm or this mindset of when you hear about Kafka, you think large data centers, maybe cloud environments, large on-prem clusters. And think about that you can deploy Kafka not just in the clouds, but also down in the dirt. So it could be, again, at the far edge, the thick edge, but think about what you can do in the power of stream processing at those edge devices. And this is real, right? So if you look on the right side, that is me. I'm at an Army command post. I'm working to deploy Confluent on a snowball device that we're going to use for aggregation and sensor aggregation at that command post, ultimately pushing it up to the cloud. I'll dive a little bit deeper into that use case specifically. But this is real, it's not just slideware. We also talked about, Kafka. When you think about Kafka, you think about a cluster, right? Kafka is designed to be a horizontally scaled cluster. You continuously add on as throughput increases, but that's not necessarily the only use case for it. When we look at these thin edge devices that may have size, weight, and power, it becomes an opportunity to look at deploying stream processing there. So we can scale down Confluent to just a single broker deployed on those edge devices. Very slim footprint from a cluster perspective. We've also been able to deploy Confluent at, say, a Raspberry Pi. It's a really small commodity hardware device, very powerful, or a tactical credit card size compute platform. Also compiled and tested on ARM processor. So anywhere ARM supported, again, typically at the edge, we can deploy Confluent. And you really start thinking about how you can unlock some of these smart edge considerations. Look at it potentially as like a downrange flight recorder. That again, it's recording all those transactional things. You can play them back whenever you want. Uh, Talked about some use cases in the past where it may be deployed on an aircraft collecting a bunch of sensor information that acts as a flight data recorder now, and then you can bring that back, upload it, or again, use something like cluster linking. So when it pulls in, it'll automatically send that data up to a cloud environment. So downrange flight recorder, but you also now get the power of, say, pub sub or just stream processing in general. And then lastly, you have that immutability from a mission perspective that can be critical. The other thing that is kind of a nice happenstance with cluster linking is start thinking about more intelligent edge processing. Now, traditionally, Kafka doesn't have the concept of, say, topic prioritization. But what you can do with the combination of cluster linking and just general how Kafka is designed is you can start monitoring the lag for individual topics. And that lag will inherently increase as your bandwidth's constricted or you have a disconnected use case. But let's talk about more of the bandwidth restriction. So as that pipe gets smaller, you obviously can't send as much data. If you monitor individual lag for topics and say a lag increases for one that you may deem as a higher priority topic, you can easily use cluster linking to turn that mirroring off for, say, your medium and low priority topics. As that data is pushed up and the lag decreases, maybe your bandwidth increases, you can turn the medium and low priority topics back on. So again, it's just another way of thinking about what you can do at the edge that you just don't want to flood. Not all data is created equal, right? Some do have higher priorities. So there are ways to manage that via cluster linking. All right, we'll get into some use cases and how we're using this. Again, these are pretty high level, but happy to answer any questions on any of these. Um, This is one that I built, or it's just a demo that I had. A couple different, 3 different Raspberry Pi devices running, and then I had was using my iPhone as a sensor also. The Raspberry Pi devices had a CO2 sensor, so it would just alarm if CO2 was high. I was also using it for a Bluetooth tracking capability, so I knew what sensors were around me. And then lastly, on my phone, I was using it for the accelerometer and some of the GPS and a bunch of other information that I can gather and push that up to a localized Confluent running on another Raspberry Pi. So it was acting as a data aggregation point. From there, I was able to cluster link to Confluent Cloud, where I was able to now get more of a view across. I had many of these running, uh, but look at how I can aggregate that data, enrich it where I needed to, but push it to a dashboard where you see down here. So in this case, I was using Grafana. So anytime I would move my phone, you would see updates happening in that Grafana dashboard. And then the one on the right was more of a data aggregation for all my Bluetooth devices that I was seeing at a conference where I was running this. So high level example there. A little bit deeper, some things we're doing, some of our partners and customers. So we were working on autonomous vehicles, in this case, large drones that had a higher payload. Uh, they were being flown out to be able to collect a bunch of different information, imagery, you name it. That was coming back to Confluent where we were running on a AWS Snowball at the time. That was being used for again propagation up to a cloud environment where they're doing deeper analytics and things like that. This is a really intriguing use case that's being used more on the Space Force side, where we're collecting radio frequency information from these edge receivers, satellites, and things like that. All that RF data is being collected again at the edge and being sent up to a cloud environment where they can do deeper analysis on it, build waterfall UIs, do digital spectrum analysis, and just start building some models for signal detection, things like that. So all those satellite images or satellite receivers, space stations and things like that, ground stations are being used to collect that information again and push it up to a cloud environment. And the last one before I dive into more of what we're doing with Databricks is an Army use case. So in this case, we had Confluent running on another AWS Snowball-like device at a command post. We had Confluent deployed on a Raspberry Pi-like device that was being soldier worn, and they were collecting any information as they went out on mission. Uh, in this case, it was DDoS, right? Because they may go dark for intentional reasons, or they're just too far away from the command post, don't have satellite comms. But in that case, Confluent was still being used to collect that information offline. When it came back up to the command post, it would automatically sync up with Confluent running there, and then ultimately up to a cloud environment where, if you're familiar with TAC or ATAC, we were feeding that information up to those environments. All right, last use case. I'll dive a little bit into this. This is our partnership with Databricks. This is more of a naval logistics use case here and predictive maintenance. So we recently announced a partnership probably about 6 months ago, and it really is a natural partnership with Databricks. If you look at where Confluent mainly focuses from a stream processing perspective, it is that operational state. And by that, I mean where data is and the information is more static. It could be databases, but you also have that real-time information. That's more of the operational state where Confluent is using our connector ecosystem to be able to connect real easy, bringing that data in. And then when you look at the analytical state where Databricks is a massive powerhouse, pushing that data to Databricks where you can do now model development, artificial intelligence, use it for data warehousing capabilities, and getting more business and BI intelligence out of that data. So it is a really good partnership between the operational and analytical states and natural fit from a streaming perspective to the analytical state. When we look at it from a naval predictive maintenance use case, there are some things that we really wanted to focus in that are challenging in this case, right? So we talked about a naval ship being an edge device. In this case, again, it is because can be disconnected, so you don't always have that connectivity. you have a lot of legacy systems running on these ships. So interfacing with them, being able to get that information out is pretty critical. One consideration also is how do you handle updates to the ship? So how do you do over-the-air updates? In this case, we're talking more about maybe models that have changed or been updated based on the data, the real-time data and legacy data. So how do we deploy those updates to those models over the air so you can get them running at the ship? General ship to cloud environment, right? Like I said, DDoS is a big case here. So how do you handle that connectivity? And then the last critical piece is how do we get these analytics that are being developed in Databricks to be running at the edge? Busy chart. Let me walk through it here step by step of what we're trying to do, right? So again, focusing more on that operational state. In this case, it's turbine information running on a ship. So many different turbines running, getting that real-time sensor information from there. You may also have, say, something like a turbine parts database. It's more static data, but ingesting all that static data and that real-time data into Confluent, again, running on the ship. We need to get that data up to the cloud where we can do deeper analytics and maybe joining that data with a larger set of historical data or parts, for instance, from a predictive maintenance perspective. So bringing that enterprise cloud data into Confluent, joining that with the ship information, again, potentially hundreds of ships in this case, ultimately doing that via cluster linking, pushing that data to Databricks where they can ingest that data. So a couple different points there, right? Databricks has a Kafka part of it already, so you can pull that in pretty quick and easy. We do have some connectors available. Table flow, if you've heard about that, is a big piece in Confluent Cloud to be able to get all that Kafka information quick and easy to Iceberg format. So a bunch of different ways, depending on what you want to do and how you want to do it. Once that data, again, from a historical and real-time perspective, is flowing into Databricks, you can use something like Delta Live Tables to build out your models using ML flow, potentially dashboarding from, say, a global perspective now, looking at which ships are fully operational and need maintenance, start doing some more mission planning in that case. Ultimately, when you have that now combination of historical and real-time information, you can start updating your models. Once you have them built, it's a matter of getting them back down to the ship. So in this case, there are a couple different mechanisms to do over-the-air updates. I won't dive too deep into that, but there are ways to do that for sure. These are typically smaller model updates that may occur, so we can get those deployed pretty easily. Once you have them on the ship, a couple different ways to run them. You can do them as more traditional microservices where it's more of a producer-consumer type of model, right? Consuming that real-time data, producing back to real-time inference, or potentially embedding that into something like Flink, where you can get real-time inference also. So that's the end-to-end pipeline. Again, a good partnership with Databricks, a natural thing to occur here, and it's really starting to pave some ways. So a quick, if you're curious how to get started, just want to point out some things, right? We have a really, really good blog written by our awesome field CTO, Will LaFaris, and our incredible engineer, Victoria Needham, who dives really deep into edge and edge compute. So recommend looking at this blog. It has a bunch of different other references at the bottom of it where you can get more information from Kai Werner and folks like that have done deeper writings on say edge computing, but it's a great start. And if you really want to get hands-on, I highly recommend going to developer.confluent.io, get more familiar with Confluent, both Apache Kafka and Flink, but it's a great starting point to get hands-on and dirty. And with that, I'll leave it to some Q&A.
Thank you, Mike. The first question we have in the chat box is, what are some of the architectural considerations when deploying Confluent at the edge in disconnected or low bandwidth environments?
Yeah, I think hopefully I covered a good amount of that, but honestly, it really depends on what your edge environment looks like. So a couple different things. I mean, requirements always come to play, but hardware is going to drive everything. When we talk about that thin edge, you really have limited hardware. So what can you do from a deployment perspective? You may have to do some trade-offs, like I mentioned. From a Kafka perspective, like running a single broker is going to get you that scale that you need, but you're trading off something like high availability. So it's always something to consider. As you get up to the stack where you have again more compute and storage, you can do a little bit more. You're still limited, but those are the biggest considerations: those size, weight, and power requirements, and what you need to do at the edge.
Thank you. The next question is, what are some real-world mission applications where edge streaming has made a measurable impact in the defense or space operations?
Yeah, good question. So, um, we led this talk off by saying, the cloud computing's obviously been there and is super powerful, but when we look at the edge and really understanding more the importance of those edge use cases, we're seeing things like in the defense world where I talked about that Army use case. Um, detail is a massive factor. So it's becoming more and more necessary to have all these sensors being collected at the edge where you can get that real-time inference. You think about mission deployments and having continuous operations, right? More informed, enhanced situational awareness. The edge becomes critical. In space operations, I give that example of Space Force, right? So collecting all that ground stations, there's hundreds of thousands of ground stations. So being able to get that information up to, say, a cloud environment is critical. That's where you start thinking about the stream processing at the edge. So Space Force is a big player in that.
Thank you. The next question is, what is the LOE to look at deploying Confluent onto JBCPs on HMMWVs and LMTVs, really an edge vehicle to support real-time tracking?
Yeah, sorry. I can't see the screen for some reason. Oh, there we go. All right, let me look at that one right there.
Lots of acronyms in that one.
Yes, that's why I want to pull it up. What is the LOE to look to deploying Confluent into, okay, any edge vehicle? Yeah, that's a solid question because that's where I went into things like it really depends on the what you have running at the edge, right? So Kubernetes is extremely powerful, really easy to manage these devices, very low LOE, right? You can deploy it actually from, say, a, a cloud environment to these edge devices just using push button capabilities. Microsoft had a really good IoT management system, and we were able to piggyback with something like Docker. So the LOE is not difficult at all. What becomes difficult is managing the hundreds of thousands of edge devices that you may have, and you really need to consider how you're going to do that. But a bunch of different ways, and LOE can be very, very light.
Thank you. The next question that I have is, what is the capability for interagency use cases with Confluent, i.e. sensor feeds for Patriot missile systems to THAAD and U.S. Air Force F-15s, sensor feeds on the Monitor project for the United States Coast Guard and Navy?
Yeah, that's yeah, these are good questions. So I think of something like JADC2 or CDAO when it comes to mind with that question. So um, it is a player in those domains, right? Obviously, what a big powerful thing with, say, just Kafka in general is being able to be um, that normalization layer, if you will, right? So bringing information in, say, from a Patriot missile, and then normalizing it so it's considered more of a generic missile, and being able to exchange that data, much like a standardization format of, say, Link 16, right? So if you have a common standard or not, you can start integrating that data from different, say, service layers or programs, but be able to normalize it in a sense where it can interact now with other systems without having a lift on either side. So treat it like that API layer in the middle, but it has a big play in that CDAO specifically.
Perfect. Thank you. How do Confluent and Databricks work together to support machine learning and analytics at the edge?
Yeah, another good question. I mean, Databricks is incredible, right? It's a prime player in the AI operations. So, like I said earlier, it is a natural fit to be able to get data from the edge where Confluent resides, again, on-prem, wherever it is, to Databricks. So it's a really easy integration point. Um, the power of Databricks really is to be able to build those models quick and easy, right? That's why it's so powerful. Once those models are built, now you can deploy them down to, an example I gave was, say, a ship, right? Now you can get some edge analytics running and get real-time inference. Big thing to consider there, I tried to call out, is how you get those models down to those edge devices becomes critical. Again, falling back to the earlier question, you really need to think about your strategy for how you're managing all these devices and when you deploy those updates, specifically when it comes to something like models.
Thank you. I do see one more question in the chat. What is the procurement to deployment timeline on average? I know it probably depends to be operational in the environment at the edge.
Yeah, the easy answer is it always depends, especially when you're talking about procurement. Deployment, like I said, it's most of the hurdles are on, say, the security side. Um, Deployment can be super easy. Um, it really depends, right? Procurement, there's usually contracts involved, so I won't even touch any of that. Deployment, again, depending on the expertise and some security hurdles you may have to overcome. It can be quick or it can be long, but we're here to help in any case we can. We are ATO'd on many different programs, so that ATO hurdle usually is not an issue.
Thank you. I don't see any more questions in the chat.
All right. Those were good ones.
All right. Thank you guys so much for being with us today. And thank you, Mike, for presenting. We hope you all will join us for our next session, Securing Data in Motion, Working at the Speed of the Mission, featuring Ron McNeely, Solutions Engineer at Confluent. Quick and easy registration. Just scan the QR code at the top. Thank you guys and have a great day.
Thanks, everybody.